All right. So, in order to study sound, we really first need to know what it is. So, when we talk about sound from a physics perspective, what exactly is it that we're talking about? Well, when we talk about sound from a physics perspective, we're basically talking about disturbances in energy that move through a medium. So, these are disturbances in energy which move through a medium. Now, when we talk about energy and mediums, what does that mean? So, what is a medium? I should know this, yes.
Anything that sound waves can travel through?
Anything that sound waves can travel through. So, yeah. And what are some of the things that sound waves can travel through?
Air,
Air, water,
not a vacuum.
anything that's not a vacuum, pretty much. So, anything that's got molecules, it can travel through. So, a medium is basically anything that's got molecules. So, the most common things that you'll travel through are air or water. Usually, when you're listening to things traveling through air. But really, any medium that can transmit and carry energy, it can be a medium for sound waves. Now, when sound travels through a medium, there's two different ways in which it travels. So, different types of waves. So, there's the two types of waves are transverse and longitudinal. And the two different types of waves have different types of properties, and they're used in different ways, so they kind of transmit waves differently. So let me show a graphic here to help visualize the difference, and then we'll talk about it. Okay, so here's a picture of both transverse waves and longitudinal waves. Now, in this case, it's a spring, but the principles still apply equally to sound waves. So if you think about a spring naturally, if you're not doing anything to the spring, the natural position for the spring would just be to be straight, right? So this would be about as straight as I can draw anyway. So this is going to be the natural position of a spring, right? So with a transverse wave, what you notice is that as you wave, in this case, a spring, the wave is going to move from the hand down to the wall and back and forth, right? But what you notice about the actual motion is even as the energy is moving this way, the disturbance is moving which way? Up and down. So even though the motion is to the right and to the left, the actual disturbance is up and down. So with transverse waves, what you notice is that you have this behavior going on where the disturbance is perpendicular at 90 degrees or right angles to what the actual motion is. On the other hand, with a longitudinal wave, again, you have the natural position of the wave of the spring, but in this case, when you stretch or compress it, again, you have these disturbances that are being carried along, but now they're in the same direction. So the motion is horizontal, but the disturbances are also horizontal. So they're going in the same direction. So the transverse, you have the motion and the disturbances being perpendicular, whereas with the longitudinal, the motion and the disturbances are in the same direction, they're parallel. Now, when we talk about sound waves in air, which of these two is a type of wave that you encounter with sound waves in air? Does anybody know? Well, let's see what happens, and then we can see if we can figure out which of the two would make the most sense. So first off, let me give a little bit of terminology here that's a little bit different maybe in the physics books than what you might be used to. So when you talk about these longitudinal waves, the areas that are compressed are called compressions. The parts that are stretched, sometimes we call these rarefactions. So these stretched areas are called rarefactions sometimes.
I think that's in the book, actually.
Is in the book?
I think so.
Okay. So depending on what the book, if the book says rarefaction, I don't know what they're talking about. It's just these areas where when you have these waves, it's in a more stretched out region. Now, if you think about something that causes sound, like let's say a tuning fork. If I strike this, what's going to happen? It'll start vibrating, right? So let's think about, and I'm going to draw my wonderful tuning fork here. Okay, see, I can't normally draw, but that I can do. So if we have a tuning fork, if I strike it, it's going to start vibrating. Now, it's going to vibrate pretty quickly, probably faster than you can really see with the naked eye, but let's imagine we could slow it down. What would it actually look like? Well, yeah, kind of like this, right? So let me try and draw this. It's basically going to look like this, and then like this, right? Because it goes out and in, and then out, and then back in. And now it'll return to its normal position kind of in between those, right? But it's going to go out, in. So what's actually causing the sound then is going to be the air around it. So it's going to be the energy that's propagated through the air around it. So let's say for a second that we could actually draw the air around one of these tuning forks. So let me draw air here. So if I had this like pocket of air here. Okay, so naturally I have my air around my tuning fork, right? Now, as it stretches, so as the fork widens, what is it going to look like? If I now have my pocket of air, what's going to happen to the air inside that pocket? Is it going to get closer together or further apart? And why is it going to get compressed?
Because the fork moving out.
Right, the tuning fork is almost like taking up the air space, right? So now it's going to be pushing out, and therefore there's going to have the air is going to be more compressed. So now your air is going to look a lot more cluttered together. It's going to be a lot more compressed together because there's not as much space for it. On the other hand, when it's in the part of the vibration where it's kind of inward towards each other, so now if it's inward, we have our pocket of air. Now what's going to happen to the air? More spread out. There's a little bit more space for it to go, so it's going to be a little bit more spread out, right? So the molecules have a little bit more room to work with, so it's now going to be a little bit more spread out than it was. Now, as it keeps doing this, what are we going to see? Well, if we could just kind of draw a huge pocket of air. So as it vibrates, we're going to have pockets where it's really close together, right, from the one part, and then as it moves in, it's going to be a little bit more spread apart. But then as it keeps vibrating, it's going to keep having that same type of motion, right? So it's going to keep coming in, so you're going to have pockets where it's really close together, and then pockets where it's a lot more spread apart, right? So now these pockets are being moved through the air, right? So you've got these pockets where it's all clumped together, and then these pockets where it's more spread out, and then there's pockets where it's close together, and pockets where it's spread out, and it's kind of moving across the air, right? So if we think about that, which of these two types of motion does that seem to be describing? The longitudinal or the transverse?
Longitudinal.
Longitudinal. So the air waves are actually going to move in longitudinal waves as the sound waves are going to move in longitudinal waves as it moves through the air. So it's longitudinal waves that are going to be transmitting the sound. Now, if we were to look at sort of a graph of these pockets here, if you look at how compressed they are versus how spread out they are, and you were to try to make a graph, and I promise I won't do very many graphs because I know that Some people are probably getting a little bit anxious already, maybe starting to sweat when I said graph. There won't be very many, I promise. So if we were to try and graph this, so the compression versus time. Well, the natural state would be if there's no compression or stretching, right? So what you notice is that you have places where it's got a lot of compression, more than usual, and then it kind of comes back to normal, and then there's very spread out, so there's very little compression. Then it comes back to normal, and it's back to being very compressed, back to normal, low compression. So it has this sort of shape to it if you were kind of looking at how compressed and how stretched out it is. And we'll actually see this again later on. So just something to keep in mind is, we have this sort of pattern here with the compressions and the stretchings. Now, when sound travels through air, it travels at a certain speed. Now, does anybody happen to know the sound of speed in air? If not, it's okay. I'm just curious, one of those tidbits. No? Okay. So in air, now, when I talk about the speed of sound in air, there's actually another factor that's going to make a difference, not just the fact that it's traveling in air, but what other factors affect the speed of sound? Anybody know? The density of the medium. So how does that affect it?
Well, if it's denser medium, it would slow down.
Right.
Harder to waste through the air.
Mm-hmm.
It's more spread out.
Right. And what else? So the density makes a difference. And what do you mean by that?
By like other objects or other different mediums.
Okay, so like if it interferes with other mediums, like it starts in air and then it reflects off of some one medium and then off another medium, that's certainly going to affect it. Anything else? What about temperature? That make a difference? Yes. I wouldn't have asked otherwise, right? So, yeah. So temperature also makes a difference. So when we talk about the speed of sound in air, typically we talk about it being at around 70 degrees. So in air at 70 degrees, the speed of sound is either 1,228 feet per second or 343.8 meters per second. Now, notice that when we talk about the speed of sound here, so this is talking about air, but really whatever the medium is makes a difference, and the temperature makes a difference. Notice we didn't say anything about the actual source. So the speed of sound does not depend on the source. So it doesn't matter if it comes from a tuning fork, it doesn't matter if it comes from a drum. If it's traveling through air at 70 degrees, it's going to travel at the same speed. So the natural question then is, what effect does the actual source have on the sound? What does that have to do with it then? So is everybody finished copying? Because I got to go to the next page. Okay. Well, let's think about tuning forks. So let's say we use these two different tuning forks. What's going to happen, or what's going to be the difference if I strike each of these?
One will be lower pitch, and one will be higher.
One will be lower pitch and one will be higher pitch. Now, what does pitch mean? And we use the word a lot, especially in music, but what does that actually mean? The frequency of the wave. Is that what you were going to say?
Yeah.
Okay. So the frequency is going to be different. Now, what does frequency then mean? Because we're kind of using all these technical terms. What does that then mean?
When you're measuring like intervals of the wave, is how many pass certain.
Right. So how many waves you're going to have in a certain time span. So the source makes a difference in the pitch, right? So with the source, the source when you look at the frequency, that affects the pitch of the sound. And so if the source is vibrating faster, is that going to have a higher frequency or a lower frequency? Higher, and why is that?
Vibrating faster, you're gonna have more waves to shoot.
Exactly. So if it's vibrating faster, you're going to get more waves in the same time, so it's going to have a higher frequency. So faster vibrations, faster. So faster vibrations cause higher frequency. So when an object emits a sound wave, it vibrates, right? So the vibration is causing the sound wave, but it continues to vibrate. So when we hear these vibrations, if those vibrations happen on some sort of regular pattern, so if you have regular, or let's say regularly occurring vibrations, then this is called periodic motion. So when things happen with regularity, it's called periodic. And when it has this sort of period, that's when you hear the sounds, that's what kind of is interpreted as music. It sounds good to your ear when it's periodic. When it's not periodic, so not regular, so we call that aperiodic. So if it's not regular, we call that aperiodic. And that's more interpreted as noise. It doesn't sound very good when it's not regular. Now, when we talk about these waves, in the periodic or aperiodic waves, some of the properties are what's really going to make a difference in what we interpret. So we just talked a little bit about the frequency, and we'll talk about it a little bit more. But really, there's several properties that we're going to want to talk about that are going to affect sound in general. So when we hear different pitches, that reflects different frequencies, right? So we talked about that already. Now, when we talk about, let's say, instruments, so if you have a wind instrument, and actually let me insert a picture here. Okay. So when you have a wind instrument, you cover up the different number of holes. How that affects the pitch, but why is that, or how is it that that happens? Well, what you're doing is you're changing the length of, like the amount of space that the air has in order to travel inside the instrument, right? So if you have more length, what's going to happen to the frequency?
Lower,
And why would it be lower?
because they're more waves in bigger space.
So you have more, it's got more space basically to travel through, right?
Mhm.
So, and as you can see kind of here from the picture, so in the first one, if you cover all the holes, and then in the second picture, the first 5 holes are covered, and then the third picture, the first 3 holes. So you see that the amount of space that you have is changing, right? Well, the frequency, because it's got a different amount of space to travel through, is going to be different, and therefore you're going to have different pitches. And so, as I mentioned, you can see from the picture here, when you cover the first 3 holes, so there's a very short space, you're going to have a higher frequency, right? It can occur more often because it's got less space to go through. As you cover up more holes, it's got further distance, so it's not going to occur as regularly or as frequently. And so you have a different pitch there. So the pitch affects things like musical instruments, or the frequency affects musical instruments and the pitch that you're going to get from them. Now, I also, to kind of demonstrate this, found this demonstration online. So just so we can kind of hear some of the differences. All right, so I think, let's see, this is representing the 88 keys on a keyboard numbered from left to right. So that probably makes a lot more sense to you guys than to me.
Mhm.
So the 49th key is an A key. So if we play this, that sounds like an A.
Yes.
Nate has
Sure, right?
perfect pitch. So
Huh?
Nate has perfect pitch. So
Oh, okay.
Yeah.
Okay, perfect. Sounds good to me. So, okay. So there's an A note. And you see here the frequency is 440, right? Now, if we were to change this, so I think that it says here that 40th key would be a C note. Well, the frequency is lower. So what should happen to the sound in terms of the pitch? A little bit lower. So let's see. Sound like a C?
Doug, can you find a C that's an octave above that so they can see that the frequency changes, but the wave, like what happens?
Oh,
Does that make sense?
yeah. Do you know?
I don't know which key. that
Does
is.
anybody know?
Let's see. If A is what, the 49th?
Ninth, yeah.
52?
52. There we go. That okay. You have to tell me. I am not really. I don't have an ear for that.
So can you explain why that's a C,
Uh-huh.
just like a C an octave lower? Obviously, the wave changes because
Yes.
it's a higher frequency, but the pitches actually sounded the same, only an octave apart.
Right. So you're saying. So here, the C. That was also a C,
Mm-hmm.
and so.
Does that have to do with the amplitude of the wave?
We haven't gotten to that, but
Okay.
oh yeah. So yeah, the amplitude will affect also the way that you perceive the sounds. So yeah. So we could listen to different ones, but you can kind of see how the wavelength changes, and as the wavelength changes, you hear differences in the pitch. Now, another important property, we're going to get to that, is the amplitude. So, oh, we can't see that. There we go. Amplitude. So, what exactly does the amplitude tell us?
How loud or sorry.
Go ahead.
No,
Yeah.
that was a question.
Yeah, go ahead.
How loud or quiet something is?
Right, so it's going to affect the intensity. It's about the amount of energy in the sound. So amplitude affects is the amount of energy or the intensity. And that gets interpreted as how loud it is. Now, there are other factors that affect how loud a sound is, such as frequency. So different frequencies with the same intensity are going to sound different. And I actually do have a graphic for that, which so when we talk about the amplitude, and we'll talk a little bit more, kind of get into a little bit more of the details in a minute about the actual intensity and the how loud it sounds. But the actual intensity also is, and how loud it sounds is affected by not just the amplitude, but also by the frequency. And so this is called the Fletcher-Munson curves. Have you guys seen these before? Okay. So basically what it's showing is that the tone that you hear when you hear the sounds, how loud it sounds or how intense it sounds depends on both the intensity and also the frequency. And so for different frequencies, it's going to sound different even if it is the same, has the same amplitude. So when we talk about intensity, how is intensity measured? Well, the intensity is measured in decibels, which is abbreviated as dBs. So this is kind of a measurement of the energy that the sound wave has. Now, decibels in and of themselves are meaningless without some sort of basis for comparison. So intensity measurements in decibels require a basis for comparison. So normally intensity is measured as power divided by area. And again, I won't get into too much math or formulas about that, but it's normally measured in watts per meter square. Decibels is a little bit more convenient to use, and so we usually use decibels, but it requires some basis for comparison. So does anybody know when you measure things in decibels, so it's a comparison, what is it compared to? What is sort of the standard for decibel measurements? Anybody know? So the standard for comparison for decibel measurements. Well, it's actually the threshold for hearing. So it's the threshold for hearing, which is in terms of actual power, it's 1.0 times 10 to the negative 12 watts per meter squared. So it's kind of amount of power in a certain area. Now, again, we don't usually measure things in watts per meter square. You're more used to hearing things in decibels. So one thing that's useful, and the only calculation we'll do, right? Yeah, the only calculation we'll do is try to figure out how you go from these kinds of intensities to actual decibels. So if you want the decibels, you take 10 and then multiply by what's called the logarithm, and then you take your intensity and divide it by the standard here. So I'm going to use I0 to kind of represent this standard. So this is the standard intensity, the threshold for hearing. So you take the intensity of whatever sound wave you have, divide by this number, and that tells you the decibels. So let's say, for example, you had an intensity of 1.0 times 10 to the negative 11 watts per meter squared. And again, that looks strange because you're probably not used to seeing it in such terms. Well, that level of intensity, if we were to convert that into decibels, so in decibels, that's 10 log, and then if you just plug in your numbers, well, again, if you don't know what log is, don't worry too much about it. It's pretty standard on a calculator, so just plug it into a calculator. So if we did 10 times the log of 1 times 10 to the power of negative 11 divided by 1 times 10 parentheses here. Get this right, sorry. So 10 to the power of negative 12, of course. Well, I'll just tell you the punchline. Forget that. So this actually ends up being 10 decibels. So what we've done with the intensity is we've increased it by tenfold. So it's 10 times greater intensity, and it causes a decibel increase of 10. If we were now, instead of increasing the intensity by 10, if we did it times 100. So in other words, if we had an intensity of 1.0 times 10 to the negative 10 watts per meter square, when you plug that in, what you end up with is 20 decibels. So every increase of 10 decibels actually increases the intensity, the energy of your sound wave by tenfold. So if we wanted to know the difference between, let's say, the difference between let's say 40 decibels and 50 decibels, that difference of 10 has 10 times the intensity. Or the difference between, let's say, 40 decibels and 70 decibels. So each 10 is a tenfold. So in this case, there's 3 tenfolds, right? So 10, 100, 1,000 times more intense. So when you're looking at decibels, you're actually not just talking about a normal increase in intensity, it's multiplication, it's tenfold. So every 10 decibel increase is actually 10 times more. So 10 increase is 10 times more intense, 20 is 100 times more intense, 30 decibel increase is 1,000 times. So it's on this what we call a logarithmic scale. So when you look at these decimals, small increases in the decibel calculation is actually huge increases in the actual intensity of the sound. Now, another property of the waves that's important is what's called the waveform. So what the waveform basically refers to is the shape of it, the shape of the wave. Now, if we want to understand the role that waveform plays, let's imagine that you take a string, you hold one end, and then you tie the other end to a wall or something. So let's say you have a string that you're holding that's attached to a wall. So there's you, and there's your string. Okay. So if you take that string and now you were to give it a flick, what would happen? You get like a wave going, right? So if you now give it a flick, so give the string a flick, then you end up with sort of a wave going on your string, right? Well, as you do that, the wave travels to the end, and then what happens? It comes back, right? So it goes to the end and then travels back. So it's going to reflect. As you get these waves going, they can interfere with each other. They can help each other out. So, and we'll get into that. I don't think we'll get into it today. So probably on Thursday, we'll get into sort of interference of waves, reflections, refractions, things like that. But the basic idea is that you're going to get the wave traveling to the end, gets to the wall, reflects, and then travels back. Now, most of the time when you do that, you're just going to kind of get these jumbled up waves. But if you were to flick it at exactly the right frequency, so flick it just the right way, what would end up happening is you get a wave that as it goes, and then the one that comes back, they're going to kind of be in harmony with each other, going to be kind of synchronous with each other, and we call those standing waves. So when we talk about standing waves, it's basically that these waves, they form this pattern that is kind of constant throughout. So it's sort of the pattern that is constant. Now, at some points in the rope, when you have these waves, and actually, let me put a picture here and then I'll talk about this instead of the other way around. Okay. So these are some examples of some standing waves. So the first one, you flick it, the way it travels and comes back, it's going to look almost like it's not moving because it's in synchrony. And the other one, you have two flicks, so you've got these two, they look like loops, and as they go and come back, it kind of looks like it's standing still because it's in synchrony. Well, some of these points are going to look like they're not going to be moving at all, right? So like if you look at this point here and this point here on this wave, or on the second one here, here, and here. These points are not moving at all because of the interference and things like that. So we call these points nodes. And then the points where you have these sort of peaks to them, so these kind of high points and low points here, we call these antinodes. Now, it turns out that these nodes or these antinodes occur with certain regularity, a certain distance apart. So nodes and antinodes occur at half wavelengths. So they're kind of half wavelengths apart. And so if you get this just right, you can get these kind of going, and then it kind of looks like it's not moving, it's descending waves. But it turns out that when these occur at these half wavelengths, there are an integer number, and by that we just mean 1, 2, not like a half of a wave or a quarter, an integer number, so like 1, 2, 3, so on and so forth, of these. And so if you get the frequency right, you can have these occur. And so these frequencies, so the frequencies at which these occur are called natural frequencies. Now, these natural frequencies, there can be more than one. So like here you see that there's a frequency that causes it to have one loop, and then a different frequency has two loops, and a different frequency has three loops, so on and so forth. The first one is called the fundamental frequency. So the fundamental frequency, or first harmonic. So it's a frequency that causes this one single loop in the standing wave. Any of the frequencies after that cause these standing waves but with more than one loop, we would call second harmonics, third harmonics, fourth harmonics. So if you can get the flick with just the right frequency, that way you get these waves, that's where you get your harmonics. So here we have the second harmonic, or sometimes I think it's called the first overtone. So this picture here would be the third harmonic, or the second overtone. So the frequency that these waves travel, like so how frequently they occur. To get it just right, you get your harmonics and your overtones. Now, this is all good because we're talking about you standing with a rope, flicking it, when one end is attached to a wall, but where does it actually occur in music? Because obviously you don't make music by holding ropes attached to walls and waving them, so where would this actually come in actual music?
Well, guitarists often they can even tune really good guitarists
Uh-huh.
by tapping the string just right, and they can tune to with the harmonics.
Exactly. So things like, well, stringed instruments in general, right? So you have the two ends that are attached to something. So maybe you're not holding it, maybe it's not attached to a wall, but when you think about like a guitar or a violin or even a piano, you got the two ends that are attached, and what happens when you hit it, it causes the waves. And if you get the hit just right, you can cause these standing waves, and that's where you get your harmonics with your stringed instruments. So I'll stop there.
I was going to tease them that was going to be on the guitar proficiency.
Oh, okay.
Yeah. No, I'm just kidding.
So on Thursday, if you guys want to bring some instruments, I was playing with some of the equipment downstairs. I didn't quite get it working just right, but I don't know if it's because they're also doing construction up here that's maybe causing, I don't know. But we'll see what we can do. Also, I was thinking about labs for Thursday, and I realized you can't have too many groups working at the same time with musical things. Yeah, so maybe we'll do more like demonstrations or something like that. But if you guys want to bring some instruments, we'll see what we can do in terms of trying to, maybe reproduce these, look at how the actual frequency, like actually get the graphs of the frequency so you can see, the changes and things like that in frequency. So.
And then if they have any questions, can they bring them on Thursday?
Yeah, absolutely.
Thank you so much.
So, okay.
Really appreciate it.
No problem. Like I said, this I recorded, so